Greetings to all. Thanks for joining the session on HPC and AI, two sides of the same coin. None of us has been spared from the Midas touch of these large deep learning models, which are trained using high performance computing infrastructure. We are witnessing growth in the size of deep learning models as well as the powerful high performance computing or HPC. Where will it stop, if ever it will stop? We will address this question in today's webinar with a keynote talk followed by a fireside chat with our esteemed panelists. Before that, as you saw in the introduction video, we as a researchers are inventing things but need a scientific community around to validate, review, and spread our research. So I like to invite Dr. Hemant Pandey, Executive Director ACM India, to give you a brief on ACM India and its activity. Over to Hemant.
Thank you, Rekha. Good evening, good morning, based on wherever you are. And on between TCS Research and ACM India, something we've been doing for over a year quite successfully now. And it's one of the initiatives that we have for computing people. So on that note, I'll just take this opportunity to tell you just a little bit about ACM India and the initiatives that we run for everybody in computing, whether it's student, faculty, or professionals. So don't know if you know that ACM is the world's largest computing society. Out of that, about 15% of the members are in India. And they manifest as chapters, whether it's student chapter or professional chapters, women chapters. And what I would like to invite you to do is that be part of this initiative, be part of this movement, and be members, whether you become a student member or a professional members. So if I look at the initiatives, I will broadly categorize them into 4 areas: research, education, learning and professional development, and recognizing contribution. I'm not going to tell you all about it, but we can share this with you later along with the other material that we do about this webinar. And underlying all this is our strong commitment to diversity, equity, and inclusion, which is by welcoming, encouraging participation, doesn't matter what background, institutional background, ethnic background, or your professional background, and so on. Okay, so with that, again, I would reiterate my invitation to come join ACM, ACM India, contribute, be recognized, be part of the network. Thank you, and back to Rekha now.
Thanks, Hemant. I'm sure the community here will definitely leverage what you have shared and join ACM India. So with that, now we'll start the keynote talk. But before that, I'll request audience, if they have any question for ACM India or for the webinar, please put up in the chat box. So let's start with a keynote talk by Dr. Raghu Prabhakar, co-founder of SambaNova startup in the domain of AI accelerators. And I'm fortunate enough that I happened to work with him on the research prototype of his invented system during my stint at Stanford under the guidance of Professor Jeff Fullman and Kunle Olkutan. So welcome Raghu on board, and over to you, Raghu.
Great, thank you. Thank you, Rekha, for the kind introduction. Good morning, good evening, wherever you are. Good morning for me here, and good evening for people back in India. I'm glad to be here. So let me share my screen, bring up my slide deck. All right. Hopefully all can see the screen. All right. So the title of the keynote today is now it's called Accelerating AI for Science with a Reconfigurable Dataflow Architecture. Termed it as AI for Science because, as we'll see, the boundary between what we're calling as AI workloads and what we're calling as HPC workloads is kind of blurring. But it's creating a bunch of challenges. So I'm a systems person by trade, and it's certainly creating a lot of interesting challenges when you're trying to build, train, and serve these models at scale. So hopefully you'll find this talk interesting. So this is a rough outline of today's talk. So I'll first talk about what it's taken the world by storm, which is this concept of foundation models, and what I mean by data flow, just data flow acceleration, and why really we need to go down this path and why it's promising. With that, then I'm going to talk about a specific data flow architecture that we have built here at SambaNova, just as a proof point to understand what it provides, what its capabilities are, and from a systems and research point of view, a new architecture creates a new software environment and hence new challenges. I'm going to talk about the programmability part of it, and then up level back to impact. So what is the thing that it's actually enabling? All right, so starting with the first topic, which is foundation models. As I mentioned earlier, we are sort of in a new era of AI. If we think back to, in this slide is of course saying only 2000s, but of course we all know that the ML community has been alive since more than 50 years, 50, 60 years. But the 2000s were in some sense an era of the traditional ML algorithms, like decision trees, your classic ML, so to speak. And then, once there was breakthrough in building like deeper neural networks, there was this plethora, like a model zoo of deeper ML models. And 2010 became the era of deep learning. We have all the various kinds of networks, AlexNet, ResNet, pretty much all these foundational models. They came out in the 2010s. And in 2020s, what we see is a consolidation of these model architectures. So while it was in some sense like a Wild West in the 2010, we sort of see that because people have been able to train bigger models at scale, we see the model architectures converge. What I mean by that is we have these huge models. They train on a large amount of data, unsupervised. They train on all sorts of while there is still focus on data pre-processing, it trains on unsupervised data. Unstructured data, and the base capabilities of these foundation models can be used for a variety of tasks. So this slide is kind of showing a brief snippet. Your data could be from emails, voice, contracts, all kinds of textual media out there. And once you pre-train your models, they can be adapted to perform a variety of tasks, including language translation, object recognition, content generation, which we have seen has taken the world by storm recently, semantic search, and so on. And in some sense, the large language models and these foundation models are powering the next wave of discovery. So let's give 3 examples here. One of them is for images. The other one is for languages or language models used in science. And the other one is models to accelerate simulations, or models which try to predict the result of simulations, or what we call as surrogate models. So starting with like imaging, now what LLMs can, or what these foundation models can do is, before, while ResNet, for example, was trained on a data set where the images were, I believe, 224 by 224, very small images. But the scientific community has, they would like a much larger resolution. So things like seismic analysis, particle physics, medical imaging, they require effectively really, really large 3D convolution models, something of the order of 512 cubes. Similarly, on adapting the large language models for scientific research, COVID-19 research, drug discovery, material sciences, essentially they all use the same approach that languages use, because analyzing genomic sequences is effectively analyzing a very large string. So there is some transferability there in terms of technology. And finally, surrogate models. As I mentioned earlier, surrogate models are ones that replace a much more complicated component in simulating the real world. Could be weather forecasting, fluid dynamics, multiphysics simulations. The intent here is that surrogate models are used as a speed up tool, such that your simulations finish faster. Now, all these are creating, it's creating a very interesting workload dynamic within the systems world. What exactly do I mean by that? Foundation models, or what I'm calling as foundation models here, is they have grown in their size. And when I say size, I mean the number of parameters in the model. So as you can see, so we are sort of at the right end of this graph, which is sort of in the 200 billion plus era at this point, where 200 billion is already like 400 plus gigabytes of space just to hold the weights of the model. What this creates is, if these models are becoming ubiquitous and they're becoming bigger, it means that training them and serving them at scale it's almost a requirement. But that creates a bunch of challenges. And we'll talk about what those are. And it really comes down to three sort of buckets of challenges. One of them is just the sheer model size, and then the complexity of the model, where complexity is, what kind of data transformations are required, what kind of operators are there in the model, or we orchestrate data movement, and so on. And then the time itself to train them. Now, starting with just to peel back one more layer of the onion, model size here is kind of pushing the existing conventional systems that's built today to the limits. And the primary reason is, it's just the sheer capacity. If you have a large model size, we need an underlying system with a larger memory capacity. If we don't have a system with large memory capacity, we'll have to sort of shard the problem, and it becomes like it's a non-trivial engineering problem, which is available only to a few organizations. So it wouldn't be as ubiquitous or as reachable as it should be. But the issue is, well, we know how to build systems with large memory capacity. When I say memory here, think DDR. The problem is larger memory technologies are lesser in terms of memory bandwidth. So when we compare DDR to something like HBM technology, there's almost a 10x gap between the achievable bandwidth. And most of these workloads, if we aren't careful about how data is orchestrated, low bandwidth can very quickly drop your device utilization, because these devices which are compute heavy, you need to feed the beast, so it's very quickly going to drain the memory bandwidth, because of which we end up with low performance. The other part is model complexity. So there are some models where it's very, very symmetric, and it's easily analyzable, gets talked about a lot. But when we talk about this interplay between AI and HPC, there's usually a combination of multiple facets, like dense tensors and sparse tensor algebra. There's a combination of compute bound and streaming operations at the same time. So how do we determine the roofline for things like this? And along with this, there's the frequent, often less talked about, which is tensor transformation operations, like transpose, reshape, permute. They all take up time, they all take up memory bandwidth and memory resources, and they can quickly overwhelm the system. And finally, training time, which is, no matter what we do, there has to be a convenient solution where we can harness the power of scale across sockets, across racks, across nodes. But doing so requires us to think about how to partition the problem. Do we take a single model and kind of spread it out like a giant pipeline across a bunch of chips? Do we do data parallel, which is we have a batch size, we split the batch across different units, or do we do tensor parallel? All of them are, there's a big design space here. So to understand this problems a little bit more, I'm going one level deeper by just taking this toy example, and to sort of highlight what are the key problems that we face today in terms of acceleration. So this is a very simple model, a couple of convolution layers, a pooling layer, norm, and sum. There's a skip connection in the middle. So if we imagine how this executes on a traditional, like an AI accelerator, like a GPU, if you imagine time is going downwards to the right of the slide, you see that each of these operations happens one at a time, where at a given time, the operation is parallelized across the compute resources of the target architecture. So in this example, we do the first convolution, and then but in order to do the first convolution, you load the weights and the activations required. You compute the convolution, produce the result, goes back to memory. Then you load the weights again and the intermediate results again, do the pooling, put the results back to memory, and so on. So you can see that memory is serving as this intermediate buffer between any two given operations. Now, the problem with this is this can quickly overwhelm your memory system. And more importantly, these models, they don't necessarily need to be executed only like this. They are rich in pipeline parallelism. So in other words, there is no reason why we have to wait for the entire convolution to finish before starting the pool. We can sort of keep the convolution and pool and conv to executing like a data flow pipeline as we feed samples through it. It's not exploiting data locality. If we have to go all the way back to HPM and keep coming back and forth, we're not doing a very good job keeping data on chip. So this is a performance as well as a power thing. And then there's limited automatic fusion. So if we had the ability to execute these models all at the same time on chip, then we end up with a much more interesting design space. So in the rest of the talk, I'm hoping to get into that to understand what does that really enable and what are the challenges there. There's of course no free lunch, so that comes with its own fair share of challenges. So as an example, if we need to execute this as a data flow program, where if we imagine that these operators are constructed like a pipeline, and we assign some units to these operators, then we could end up with a data flow pipeline like this. So here the orange blocks are the compute nodes, and the blue blocks refer to buffers or intermediate results. So if we had an underlying system that enabled us to compile a program down into a data flow pipeline like this, then we end up with some interesting optimizations. We end up with some interesting benefits. So first of all, because you have these intermediate buffers, which can all be on chip, you capture a lot of spatial data locality. So we don't need to go all the way back to HPM. This alleviates a lot of pressure on how much bandwidth you need in order to execute a program like this. And second is there's a different levels of pipelining here. So each operator itself can use SIMD data parallelism. We can do pipelining across models because you have the batch dimension in the program. And there's even task parallelism where you can replicate the same pipeline multiple times. So you get this big design space of interesting choices. But to do so, we need like an underlying compute substrate. So if we go one level deeper, we take a single operator, something like a softmax or a layer norm. What I mentioned in the previous slide translates even here. So each of these individual operators can be composed using things like some unary binary operators, what I'm calling here is map, zip, and reduce. And communication can be orchestrated between the buffers. So the question now is how do we build something like this? So this is where we get into the SN30 RDU architecture. This is full disclosure. This is, of course, something that we work on here at SambaNova Systems. So I'm using this to drive home the advantages of data flow. So I'm going to be anchoring the discussion around this architecture. But first, why do we? Hopefully, the motivation is clear by now. Why exactly is the RDU needed? If we want to facilitate executing things in a pipelined way, like I mentioned earlier, existing solutions like GPUs, they don't give us the required flexibility in order to do this, especially with their memory system on chip. FPGAs potentially, but they have programming challenges, and ASICs. Well, the ML world is moving too fast, so we still want something flexible. So that in mind, sort of have designed the RDU, and this was announced, I think, last maybe a few months back. This is the SN30, so it's the third generation, and second generation, my bad. So it's about 688 teraflops, manufactured in 7 nanometer, 640 megabytes on chip. So it's almost more than half a gigabyte of on-chip memory. But more importantly, it can interface to a lot of off-chip memory capacity. It's about 1 terabyte of addressable memory per socket. All right, so just diving into what the architecture is, it's on the left-hand side, it's a cartoon drawing showing it's a few tiles where each tile can be independently managed. But the guts of each tile is really this grid that you see on the right-hand side, which is composed of the orange blocks, which is PCU, the blue blocks, which are PMUs, the switches, which are in yellow, and then the interface to the I/O subsystem, which is the AGs and CUs, address generation and coalescing. So fundamentally, this architecture is distributed, meaning it does not have a notion of a traditional program counter, and the execution model is different. So it's what we call as a decoupled access execute architecture, which means your compute and the memory access are effectively two separate message passing instances. So just to zoom in real quick on what the orange, which is the compute workhorse is, this is what we call as the PCU, pattern compute unit. It's composed off of a few stages, pipeline stages, where each stage is a SIMD ALU. It supports all sorts of data types, FP32, BF16. It has programmable counters. So main reason is if you think of a loop that we would like to accelerate, almost all loops have some sort of nested iterators, and whether these iterators are used just for bookkeeping or they're used for the actual computation itself, the counters act like a dedicated hardware to accelerate that. Turns out it's very convenient to do that. In addition to this, of course, there's frequently encounter operations like sigmoid, exponent, tanh, and this dedicated hardware to accelerate operations like that. But as you can see, the flow here itself is stateless. So the PCU operates on data that flows in from the left, from the data inputs, computes based on what the pipeline is statically configured, and then it outputs data on the right-hand side. So the data transformation itself happens in this unit called PMU, pattern memory unit. So here, this is effectively a multi-banked array structure. But more importantly, it has two things which I think make it interesting. One of them is the data alignment unit. So you see the two boxes on either side. They enable us to do high-speed transpose and high-speed data manipulation operations. And the other interesting thing is these address ALUs. So there are ALUs inside the memory unit to accelerate address generation. And of course, the opcodes inside the address ALUs can be different from what the opcodes of the main SIMD unit are, because address generation requires different kinds of instructions. Real quick on the switch. So this is there are three kinds of networks that enables us to route data between the PCUs and PMUs. There's two, data and control. The data has two granularities, a vector network and a scalar network. So there is it's a pipeline where the compiler can configure the switches to have any route as required, and then the switch handles the arbitration and bandwidth sharing. And finally, the address generation and coalescing unit, which is the chip's interface to the I/O subsystem. So this is similar to the PMU, but it has address ALUs to produce off-chip requests. So requests going to DDR, requests going to other RDUs, going to the host memory. So there are ALUs that can be programmed to do just that. So along with that, of course, there's since we're talking to multiple downstream entities, there is a request scheduler and there's some arbitration virtual memory unit, which is handled in this component. This is just a quick thing of saying, it's built, it's integrated into a rack, which is, built using open standards. Each socket can interface with 1 terabyte. One node is composed of 8 sockets. So there's 8 terabytes of addressable memory. And it's kind of cool. So more important part of this architecture is, I mean, we can build the architecture and that's fine. What does this mean in terms of programmability and what has this been able to achieve? So I'll go back to this example, which I briefly flashed earlier, which is, let's take softmax and layer norm. So what I've done here is, you see the mathematical expression for softmax, and in some sense, a data flow graph representation of softmax, and same thing for layer norm. So I'll just walk through how exactly you would want to map something like this onto a data flow architecture. But before that, we all know that compute matrix multiply is like the workhorse of all these workloads. So a very simple way to map matrix multiplies is, as you see in the picture on the right-hand side. If you're doing C equal to A times B, A and B can reside in two different PMUs. The connections from A and B into the PCU is orchestrated through the switches by software. The PCU does the multiply add, and the results are stored back into the PMU. Now, the other thing I mentioned earlier was we need to do this on-the-fly transpose. We need to do all these data manipulation operations. So I'll just briefly run through an example of how data alignment units enable us to transpose at full throughput. So for this example, pretend that we have this input tensor, which is 8 by 8. So rows have the same color and columns have the same number. And if you want to do transpose, we would like to change the vectorized dimension, which is we would like now to have the rows to have the same number, and the columns to have the same color. So how do we do this? And this is basically done by using a combination of multiple SRAM banks and a data alignment unit. So when you write the data in a strided fashion like this, where effectively you're writing it along the diagonal, you can enable both normal as well as transposed access at high throughput. So if we go through vector by vector, when you get the first vector, which is purple, we can write the elements of the vector as shown in the slide. When the next vector arrives, you do the same thing, except that you have rotated the values by 1. So your 0 is now rotated by 1 position, and 7 is in the first position. You keep doing the same thing. And 0 is now in the second position, third position, and so on. Which means after writing 8 vectors, you have this sort of jumbled up representation inside the memory, but there is a method to this madness. So now if you want to read it transposed, which means you want to read the first column as the row, we can still access all the banks concurrently. You see that the address pattern is different, but it is a predictable access pattern, and you do get the entire vector materialized in one shot. So you can do the same thing for ones, twos. You get the idea. At the same time, let's say we did not want to transpose. We actually wanted to read the vector exactly the way it was. That's also fine with the same representation. Because when we wrote it, we did write it such that every lane of the vector goes to a different bank. So if we want to read the purple vector as it is, it enables you to do that. Same thing with the blue. The data alignment unit on the right-hand side is correcting for the positions of these. The 0 has to be at the first position. This alignment unit enables us to do the correction. Yellow and so on. So having hardware features that can accelerate things like this, even though it's at the lowest level of detail, this is hugely beneficial because this is a key component to manage capacity and bandwidth on chip. So zooming up one level, we want to talk about how softmax, something like softmax, is implemented on the RDU. This is one possible implementation. So all the orange blocks are mapped to PCUs, all the blue blocks are mapped to PMUs, and the edges are orchestrated by software. And this is a fully pipelined implementation. This is the same thing for layer norm. I'm not going to bore you with the details, but you get the idea. But one thing I did want to highlight here is this is not the only way to implement layer norm. This is the design space exposed by the RDUs. Let's say we had an application where layer norm was not really the most critical operation. In other words, it's fine if layer norm takes more time, but we did not want to waste these many PCUs and PMUs. In that example, we can actually fold it. We can map multiple operations onto the same RDU, onto the same PCU, multiple tensors onto the same PMU. and do the operation in time. So in some sense, a CPU gives this time scheduling as a default, because every cycle it's doing a different thing. It's the same capability provided in the reconfigurable data flow architecture. So tying this all together, if we go back to the first picture I showed, if this is the picture that existing architectures, it represents the execution on existing architectures. One thing that the RDU enables you is, one thing the RDU enables you is this picture that I just showed on the slide, which is instead of doing it convolution, pool, and conv2 one by one, we can construct a pipeline where some number of PCUs and PMUs are doing conv. They produce a result into a bunch of PMUs, and then that is immediately consumed by the pool and conv2. It's like a data flow pipeline on chip. But because of this, the bandwidth required off chip is only to load the sample. It has to match the rate of all the convolution and sample and pooling layers. And this drastically reduces, it drops the bandwidth, but at the same time helps us keep the utilization up. So there's been research, and Rekha and I have had the privilege of working on one of these problems with Professor Jeff Ullman and others. Spatial data flow architectures have been used in all sorts of domains. We worked on accelerating SQL queries with data flow architectures, accelerating sparse models like GNNs, accelerating larger models, which is the topic of this conversation, and scale out, which is how do we do model parallel, data parallel, because the scale out problem is pretty much the same problem as mapping these on chip. It's a distributed problem, but at a different granularity. Okay, so now I'm going to talk about some impact. What has this enabled us to do, and is it really worth it? So, as of this talk, SambaNova is deployed by multiple US national labs, where it's being used for all sorts of things, like COVID research, biomed simulation, cancer research, drug discovery, and the traditional language translation, computer vision, you name it. There are a few papers where we have jointly published with these national labs. There's some links at the bottom if you're interested. So the main thing is, I published the teraflops number earlier, and if we do the math, the teraflops number between RDUs and GPUs is not 6x. It's actually less than that. But the combination of being able to do data flow execution, it keeps the units busy. It enables us to invent or come up with newer ways of doing things, newer ways of training things. So this combination, this vertically integrated approach has enabled us to train GPT 13 billion 6 times faster than the publicly available benchmark from NVIDIA's A100. The other things are there's a bigger model. There's in addition to bigger models, there are bigger images, bigger sizes. So instead of sticking to smaller images, the scientific community is really interested in the big images, like 4K to 50K convolutions. These are enabled out of the box, and this is a sheer capability exercise. So why are big images useful? Because this is a paper we published with believe Argonne National Lab, and this is a paper on Cosmic Tiger, which is the higher models you get more accuracy. Just another example here, which is if you have a bigger image to play with, problems with GPUs or HBM-based architectures is that it's going to run out of memory. But with bigger patch sizes, you will actually get with bigger memory, you won't run out of memory. I mentioned something about seismic data used in geological studies. which require these huge 3D convolutions, which is simply not possible today on GPUs without a significant engineering effort. I'm going to skip this. Finally, going back to the sort of the traditional scientific applications, density functional theory, finite differences, molecular modeling. These are all data flow problems. We actually worked with one of the national labs where they had a very interesting model. They used a traditional neural network, and there was a sparse module and a dense module sort of connected side by side. The nice part about this data flow architecture is it enables you to fuse operators natively. Just by executing them as a pipeline, you kind of get the effect of a fused kernel for free. So there's no explicit need for someone to sit down and write like a fused op for a sparse matrix multiply and dense matrix multiply. It just happens as an artifact of execution. And finally, for a surrogate model, it's the same idea. There's this paper we published. It's on this Bragg-NN model. The key thing I wanted to highlight here is the picture on the right-hand side, where there is a forward operation and a backward operation that's fused into one pipeline. And this is replicated multiple times in a task parallel way. And this has enabled us to get some strong scaling. I mean, a single RDU itself was 8 times faster. And of course, the benchmark here is Volta. And we're able to achieve a strong scaling of 0.6 as we went from 1 to 8 RDUs. So I want to conclude here by saying, foundation models are here to stay. They're bridging the gap between what we call as an AI and HPC workload, but training them at scale is a challenge. Serving them as well as a challenge. Conventional systems have we run into all kinds of problems, which make it a non-trivial engineering exercise. And there is a lot of promise with data flow architectures to effectively be the platform suited to accelerate these kinds of workloads. Of course, SambaNova, if you, this is a shameless company plug. If you want to learn about the company, there are these links. Please feel free to visit them. We're on all social media platforms. And with that, thank you. Thanks for the opportunity. Over to you, Rekha. Rekha, I think you're muted.
Rekha, you're muted.
Rekha, I think you're muted. Sorry.
I'm sorry about it. So thanks, Raghu, for this insightful talk. I'm sure people have learned a lot from this, looking at the advanced state of HPC, and it has further ignited the fireside chat. So let's keep the momentum and move forward for the panel discussion. Audience, please hold on to your questions and share it in the chat window. Raghu is joining us for the fireside chat as well. So we will take all the Q&A at the end. So now to start the fireside chat with our esteemed panelists, I like to invite them one by one. And each one of them needs no introduction to HPC community, I'm sure. So I would like to welcome Raghu again for the panel discussion. I would like to welcome Yogesh from ISC Bangalore. I would like to welcome Preeti from IT Kanpur. I would like to welcome Sparsh from IT Roorkee, who is also a research advisory with TCS Research. Welcome panelists on board.
Thank you.
So we have been witnessing enormous growth, both in building powerful accelerator of systems for AI as well as a large model for solving complex tasks, as we just saw in Raghu's talk. Now I would request each of the panelists, starting with Yogesh, Preeti and Sparsh, to share their few lines. How do they perceive this spiral growth? So let's start with Yogesh.
Thanks a lot, Rekha, and thanks, Raghu, for a wonderful talk. I learned a lot from that as well. I have a sort of a few thoughts from my soapbox, right? So definitely deep learning and all the language models and foundation models we've seen recently have been remarkable, right? So I think last year when ChatGPT came will probably be a sort of point that we recognize in IT history, right? Going back that this is the day that things changed, possibly, right? But that being said, right, what we have to sort of, I'm always a little bit of a skeptic, right, in terms of how far things will dramatically change versus incrementally change. So we have to see whether it's going to be a complete transformation or it's going to be an under blip in the radar, right? And do we really, the other question is, do we really need to be training these models at such large sizes repeatedly, right? Right now it's an arms race, right? So you probably have maybe a few companies, maybe a dozen companies, which are literally competing with each other for survival in some senses, right? But is it going to be a scenario where we all, like if you talk about search, you talk about Google, right? It becomes a de facto standard. Are we moving towards that, right? So those things remain to be seen in terms of how much compute load is going to go on to the large-scale HPC machines, more from these language models perspective. Are we going to start from one and just retrain it, and that might have a lower computational workload, right? So that's one thought. The other is thing, and it ties in nicely with Raghu's talk, is in terms of hardware heterogeneity, right? So gone are the days when you had to just deal with maybe an x86 or x64 architecture, or maybe a GPU thrown in here and there. Heterogeneity is the name of the game with AI models, which is both good and bad because it drives a lot of the sort of power efficiency, which is a big concern because sustainability and AI don't necessarily go hand in hand from the way things are looking. But it also poses more problems for software developers and compiler developers and so on in terms of how best to use the hardware, right? Is it only purely designed for ML-based training, or could it be used for other use cases as well? Just as GPUs came from gaming and then went on to sort of ML training, right? Could it be the other way around? Can you start off with specialized hardware for ML training and then generalize it to other workloads? And that remains to be seen. And I think it's definitely going to be interesting for researchers who are at this intersection. We are going to have a heyday for the next 20 years, right? While the dust settles down, right? And lastly, I'm also sort of, given the increasing concerns on privacy and data locality, sovereignty, and so on, it remains to be seen how far things are going to remain centralized. And is there going to be a push towards more decentralization, right? So it could be decentralization level of local data centers, regional sort of clouds or HPC hardware, or even to your smartphone and increasing hardware. That again is going to, I believe, pose an opportunity. Because the last thing that you want is some kind of a global embargo that you can't use GPT-3, and where does it leave you as a country, right? So again, interesting times, but those are some of my thoughts to get the conversation started.
Yeah, thanks, Yogesh. Preeti, over to you. Like to share your thought process on this topic. Preeti, we can't hear you. Hello. So, Sparsh, maybe you can take it up while Preeti is checking her audio system. So,
sure.
Would you like to share your thoughts? Yeah.
Yes. Yeah. So, a big thanks to Raghu and Yogesh for their kind discussion. So, I also feel this is a very interesting time for AI and HPC researchers. So, back in around 2004 or 2005, the popular saying was that if a rickshawala is going to use mobile phone, then definitely mobile phone is democratized. So now that the next question in my mind is that will AI remain a luxury, a costly affair which only companies like Google or big countries can afford, or can even ordinary people use it for boosting their productivity or simplifying their lives? So, for example, foundation models and other language models and computer vision models, will they remain a costly luxury for highly funded research labs, or will they become easy for everyone to use? For them, they also have to become cheaper and more easily available across the board. For example, when this AlphaGo was first put to use against Lee Sedol, for every match of AlphaGo, the electricity budget was $3,000. Now, for a stunt machine, it is fine. So, but for real practical use, it has to become cheaper and simpler. So, researchers like us have a big role, and of course, a big questions before us. So whenever ChatGPT answers one question for you, definitely there are many more questions coming up for researchers like us. How to solve the sustainability challenges, energy efficiency challenges, cost challenges, and so on. So I'm sure today's discussion will bring up all those questions to the fore and hopefully answer many of this and also provide future research directions. So thank you all for this.
Thanks, Parsh. I think very interesting point you have raised it. Before we get into our Q&A question, I'll just request Preeti also to share her viewpoint. Preeti, I hope. No, we still can't hear you. Maybe when we. Yeah, yes, Preeti, please. Yes, go ahead, please. Yeah.
Okay. Hi, sorry. So yeah, thanks, Rekha, and nice perspective by Professor Yogesh and Sparsh, and very nice talk by Raghu. So I'll take up from where Raghu was pointing to a lot of things that sync in with me, my thinking. So I feel that let alone, okay, HPC and AI together, how far they go and what is the future of it. But one thing that will become very important is to look at the AI workloads from a system point of view. Right now, there's a lot of emphasis on building the models, sure, but when you go to large scale data, you cannot escape the system point of view, right? So communications and memory and all. So these are going to be very important, and so there's already like some workshops on system plus ML and so on. So I think those will become more and more important. Secondly, I think, I work on a lot of HPC simulations and all, and I've seen a lot of work, really a lot of work being done on like a drastic change on how simulations were producing, the mimicking the real phenomena and trying to predict. Similarly, now AI is trying to be either combined or completely being replacing some of the simulations. So for example, I'll just take two examples. One is cancer research. There is a big project from Argonne and other national labs where they are combining AI plus the simulations to predict a few of these things. And the other is I have seen in weather simulations, they are looking at like, terabytes or even more large scale data of simulations, from those data, they are trying to predict. So that is one thing. So from data, you're trying to predict, of course, using ML and on. They're also trying to replace the main, the physics instead of making it compute intensive, HPC simulations. I've seen there's some thrust towards using AI for predicting that same phenomena. So these are some interesting angles that I thought I'll share, and I'll stop here. Thank you.
Yeah. Thanks, Preeti. I think very interesting. So we have a diverse set of panelists here. So before going to audience, I think since I'm moderator, I have a liberty to ask my question, which are revolving in my mind. So the first question I think which really get triggered when Raghu was talking of this new kind of hardware and compiler. So the question is, do we see more of software hardware co-design systems or heterogeneous system for the AI workloads, and how the compiler community will evolve to deal with such heterogeneity? And we can experience new kind of accelerator coming every month, let's suppose, and then this heterogeneity becomes bigger and bigger. And how do we debug such systems? So that's the kind of question which get triggered. And maybe I request Raghu only to start with to address this question. What do you think about this?
Sure. I mean, this is I think Yogesh mentioned this point. The best time to be in systems research.
Yes.
It's a gold mine, and these are extremely important problems, right? So you mentioned two things. There's the software, there's the co-design part, the heterogeneity part, and the debugging part. Actually, so three things. The first thing, I think it's almost a given that if we really need to build systems that can accelerate, you have to co-design, because ultimately people are still building things using silicon, and that's definitely not increasing in performance or power efficiency as the need requires. So in some sense, to be more economical with transistors, we are throwing some of the burden from hardware onto software. I mean, I'm of course oversimplifying when I'm saying this, but programming something like a traditional CPU versus programming an RDU, certainly the compiler has a lot more work to do, managing buffers, communication, all these things explicitly. I mean, one can argue that if you want a performance CPU implementation, a user is going to hand optimize sufficiently enough that they have to be hardware aware. But especially when coming up with these architectures, if the primitives, this philosophy of I'm going to profile a bunch of benchmarks and make it work, it's turning out it's inadequate. Like, if we aren't able to build a compiler, and if the compiler is not addressed as a first-class citizen, you're very easily creating an intractable problem on the compiler space by making an easier to build hardware. I mean, case in point, for example, if since I come from the Dataflow world, acceleration space, and I kind of mentioned very briefly that FPGAs, it's difficult. FPGAs are great, but the problem is it's because it has these low-level reconfigurable primitives. It's a huge design space for the compiler to explore, because of which compile times take longer, and sometimes that's just not practical. We can't wait 8+ hours for a single compile run. So that things like this, like if compile time is a first-class citizen, you would likely not come up with a design like that.
Yeah.
Yeah. So one final thought on this debugging thing is the one major problem with I guess performance and functionality debugging is if the programming model is different. Like if you don't have a program counter, then the debugging paradigm itself is different. So single stepping makes sense when there is something to single step. Like if the architecture guarantees an execution order. If it's a distributed thing, then how do we enable a debug environment? What kind of state do you really want to see? Especially when the programming frameworks are going even higher up. The gap between the architecture and this is higher up. So it's, yeah, I can go on, but let other people chime in.
Thanks, Raghu. And since Yogesh ignited this question, in his intro talk, Yogesh, what do you think about this?
Right. I feel taking it up maybe even one level higher, right? So what would be the programming interface to this, even before you get to the compiler part, right? As you get into heterogeneity, right? So nowadays, to some extent, even your PyTorch or your TensorFlows might be the interface that people are comfortable with and sort of figure out how it gets executed in the backend to other layers further down, right? But with more hardware heterogeneity, this is sort of the holy grail for HPC and computing, right? Is there one language to rule them all, right? It was supposed to be OpenCL at some point in time, and Intel is pitching their one API now, and so on, right? But having at least, but if you go back in history, one reason that Java is still the number 1 or number 2 popular language, right, is because its claims of portability, right? And whether it's important or not, people sort of buy into it and it sort of gets adopted, right? So that I think is going to be one of the key things to watch out for. I don't know if it's going to happen or not, right? But will there be one sort of unifying language for heterogeneous and parallel computing that'll make the developer's job easier, right? And the other question, and this is given that we are in the era of ChatGPT, which writes its own code, right? How much code will we have to write ourselves? This is what's automatically going to be generated for us, right? I was just at a sort of ACM event a couple of days back, and there's a notion of the role of a prompt engineer, right? Not a software engineer, where you sort of just ask the right question from ChatGPT, and it gives you code, right? And you have to give the right question to get the best code possible, right? So how much of human effort is going to go into it versus automated stuff, right? So our roles itself might be sort of as software engineers, I'd be worried about what our roles are, right? If you're wearing that hat. But as always, researchers have a fun time on the list.
Yeah. Thanks, Yogesh. And Sparsh, I read your one of survey paper where you talked of, about heterogeneous computing. So what is your thought about this question?
Yes, actually, I mean, there is no single hardware to address all the needs. Even the system which Raghu has shown there is CPU and GPU plus this RDU from SambaNova. So I definitely feel that trying for a single system to address all the need will be not fully efficient. It is much better to, again, just the point Yogesh mentioned, decentralize the design of the hardware itself, because the co-design can also be encouraged if we allow different companies to design the software for different needs, or different companies to design the hardware for different needs. Like sometimes our need is high performance, sometimes our need is privacy or energy efficiency. So one hardware may give you more of energy efficiency, one hardware may give you more of performance. That's why I definitely feel that there is no single optimization objective, there is no single workload, there is no single power budget. So heterogeneous computing will be there to stay.
Oh, yeah, thanks, Sparsh, for the question. So let me ask, I have a lot of questions actually. So let me take second question specifically for Preeti. So will AI-specific accelerator and technology have enough workload traction to stay for next 5 years? What's your thought, Preeti, on this?
Yeah, I think so. Like I said, many of the applications are being modified, changed to include AI, right? So it's not only the typical, say, image classification. Now there's a lot of different diverse workloads that are trying to use AI. So workload traction, definitely yes. And I want to share an interesting fact. So there is this list of, many of you may be aware, there's a list of top 500 supercomputers, right? They are rated based on the, like the flops, right? This is from, I think from 2000 or so. So the list, it's based on a benchmark called HPL, right? The performance impact. There is, for the last 2 years, there is another benchmark, which is HPL MXP, which combines the artificial intelligence workload also. An interesting fact is the first, so as you know, 2022, we had Frontier, which is the first exascale supercomputer. It has 1.1 exaflop rating on the HPL benchmark. When it goes to AI, the HPL plus AI benchmark, it actually crosses 6 times. So 6 exaflop it gives. So that is, why is that? Because they had actually tested, engineered a lot on the AI workloads also. And there's a whole list of systems. So all the systems on top 500 are also rated on this, this particular benchmark. So yes, definitely it's going to stay for, yeah, for some time. And the other factor is, I think, there'll be some push on also maybe designing low power AI accelerators, especially for like edge devices and so on. Yeah.
Yeah. Thanks, Preeti. I think good. Yogesh has said that ChatGPT may replace software engineer, but looks like with your comment, the system people will have enough job. Their job is secured. So good for highlighting this. So let me take another interesting question since you touched upon the edge, right? So I was recalling, I'm working from the era of transaction system. Then, I had worked on data warehousing. Then I moved my research to big data analytics. I mean, the way things keep changing, we keep on changing our area. And then we had worked on HTAP, where you looked at, hybrid system, having both analytics and transactional together. Now we are looking at this AI era, I will say, and we have model training platform. So today, many of the people are having 2 different platforms, one for, your transactional analytics, bring out the data to the model training. So do we see any kind of system which is, unified, having all the things together on a single system? And also, since Yogesh and you also touched upon edge, so that means we have now compute and data, scattered, distributed across edge, fog, and cloud. So, I mean, we see such a diversity, right? I mean, so what kind of HPC system do we expect, especially when we have such a diverse kind of architecture, especially in the case of edge, fog, and cloud? So maybe Yogesh, I can start with you because you have been in this space very extensively doing research. So
Sure,
how about
happy to. So we do a fair bit of work on the edge, and more recently with edge accelerators that Preeti mentioned, right? And I see sort of 2 or 3 reasons why edge is going to become a key player, right? So one, the gap between the edge computing capability and your sort of standard server, even a GPU server, is actually narrowing down, right? So earlier it could be sort of 100x or 1000x slower, right? Now it's an order of 10x, right? So we get to play around with some of the Jetson Orin devices, right? And that has a GPU that's almost as fast as a workstation class, a 3090 class GPU, but it's as small as a paperback novel, and it consumes about 50 watts of power, right? And so that means that you have much more computing that's available on the edge. And as more of these deployments happen at an infrastructure space, right? You're always going to have the edge in the form of mobile phones and so on, right? Which are going to be of interest, right? But to me, the infrastructure edge should be interesting, right? As cities deploy, let's say, cameras, right? They're going to be deploying possibly these SD accelerators so that they can reduce the amount of data that they have to push back to their private data centers, right? As you find more autonomous vehicles, right? That again is going to have a big tap in for the compute fabric. And 5G obviously is going to add to this mix. So that's another sort of opportunity. And the last one is from the whole privacy perspective, right? So, and data sovereignty. So edge is definitely going to be part of the solution, right? So that you don't have to move the data, you can move the model. Federated learning has sharply risen in popularity in the last few years. Let's continue to go forward in that space. So, and the other is also looking at it from how do you sort of scale this, let's say, to a city scale, right? And deal with, and how do you sort of cross regional boundaries, right? So if, let's say, India has some data sovereignty rules, can you ensure that data stays within India data centers and doesn't cross boundaries? So that means, and while at the same time, you want to train a model with data across 2 countries, right? So there again, you're going to have sort of this lateral kind of federated learning that comes into play. So I think it's not just heterogeneity in the hardware, but even spatial heterogeneity in where you run things. That's going to become important.
Well, definitely, Yogesh. I think people will have some research problems to work on based on your comments. So, Preeti, what is your experience in this space? You also have been working in the area of edge and cloud. So, what do you think about it?
I don't have so much experience on edge and cloud, but yeah. So I think so. More than HPC, I think cloud is being used. So if you if you look at these problems, for example, one particular problem is like, you have edge devices on in some of these traffic signals, and you're trying to analyze some data and so on. So I think most of these are generally sent to the cloud rather than HPC systems. Yeah, I think one of the research problems which probably may gain some traction is, so these AI models, right? They are running on, so there's a budget, right? So resource budget on these edge devices. So probably one of the problems that may be interesting is like, designing these models which are not very compute intensive, and they are able to sort of look at the, the power constraints and resource constraints and design models in that fashion.
Wow. Yeah. Thanks, Preeti. I think I'll take my last question because we have a lot of questions coming from audience as well. So what I really need to understand, as we all been talking, we need powerful HPC, sustainable HPC for the large kind of AI model. And we believe these models will keep coming up the way we have Chat GPT. Maybe tomorrow we'll have some trillion kind of model moving away from the billion kind of, landmark. Then how to overcome this HPC barrier for this good AI. And also, we believe because all of us are facing this, that AI has overshadowed our system community, especially in the students environment. Everybody wants to go for the AI kind of work, and we don't see much people working on the system. So if we don't have people, so where do we get this system people to build powerful HPC? So that's a fundamental question, we keep asking. So maybe Preeti, if you can like to highlight, continuing to that, how do you address
I
this
have the
challenge?
same. I have the same question without a good answer, but yeah, students are listening carefully. Please study computer systems carefully, because any professional who is working in ML or systems you will meet will tell you that okay, learning Python and writing ML code is fine, but to get a real understanding of how the model is working, is getting affected by the system, and especially in this era of large scale big data, right? So I mean, your memory is a constraint, your network is a constraint, everything is a constraint other than your compute, and probably you have some ready-made models. But when your data is large, you necessarily have to look into systems perspective, like Raghu has mentioned so many nice things in his talks. And yeah, so I'll stop.
Thanks, Preeti. I think we'll take another viewpoint from Sparsh as well, and then probably I'll take the audience questions. Yes, Sparsh.
Yes. So I think it's necessity is the mother of invention. So I mean, we may design very very fancy complex models, but unless they are fast enough or they provide results in the real time, they will not be usable. So there will always be need to work on systems to make the networks faster, make them usable in the real time, make them usable within the power budget of maybe 15 to 30 watts. For example, like we designed one network for image dehazing, and one of the industrial partners, they contacted us. They said, okay, we are fascinated by the accuracy, but can you show it running on a mobile GPU with real-time performance? And so again, we have to start now working on that. So our results, even very fancy results, will not be much usable unless we also side by side or parallelly work on the system side. For example, if Chat GPT were to provide results in half an hour with a half an hour latency, who will use it? So that's why I think system research will always remain important. We may recognize it or not recognize it, but it is definitely as important as the accuracy side.
Yeah, thanks, Sparsh. I think
actually, if all else fails, is one thing that I may recommend. It might be the best motivator. There's an article from Andreessen Horowitz recently about how this generative AI landscape is going to impact. And apparently the people who stand to make the most money are people building systems, because everybody wants them. So that's just simply saying.
Yeah, thanks, Raghu. I think good motivation for people around to study system side, right? So let me take now the audience question, so they are our first citizen for this webinar. So since Yogesh and Raghu, you guys have been talking of foundation model ChatGPT, Yogesh, maybe I can ask you this question. So the question is, AI products like ChatGPT 3 makes it harder to find plagiarism in assignments. You have been a teacher as well. So how should we go about it?
That's a great question that probably gives faculty more sleepless nights than anything else that we found recently, right? So I think I like I said, I'm a little bit of a sort of skeptic in sort of the revolutionary nature of ChatGPT, and this too shall pass, right? We will take it for granted and move on, right? So to me, one possibility is that this is going to be like Wikipedia, right? So when Wikipedia came, right, or became popular, right, the question is, you set questions, all the answers are there in a single page. You don't have to look at textbooks. You don't have to look at articles. There's a concise version of that on Wikipedia. So how do we deal with that? You tell students, well, don't plagiarize, do citations, don't go by Wikipedia. It could be incorrect and so on. So I think educating students in terms of what works and what doesn't work with things like ChatGPT is important, right? Because I don't think the last thing we should do is to prevent them, right? Tell them you shouldn't use it, right? That's actually telling them that, hey, you have sort of 5 senses, but only use 4, right? Because I don't know how to grade you if you use a 5th sense, right? So the role for us is to tell them that this is what it's good for, use it for this, but then use your own analysis, analytical thinking, and so on as well. The other thing that I mean, I have sort of recently started doing, right, is to actually sort of ask questions that I would say to my students, right, and get the answers for that, and show the students these are the answers that you get, right, and show them that here are the wrong answers that you get, because ChatGPT doesn't claim to be perfect, right? Just claims to generate good English with reasonable content, right? It's like a salesperson. They can plausibly sell you stuff, whether it's true or not, right? So if you can tell them that, hey, there are still answers that are incorrect, and I know as an instructor more than what ChatGPT does, right? And I can catch these. You gain their respect while still teaching them a useful skill.
Yeah. Thanks, Yogesh. I think very interesting. Preeti, Sparsh, do you have any thoughts? Because you guys must be facing the similar challenge in your, college, right, for the students.
So actually, my thought actually, see, till now I have not used ChatGPT. I'm quite a skeptic. I mean, I don't want to come down and lose all the capabilities to think. So definitely. So, but one simple way is that if I have 80 students in my class and 2 students ask the same question to ChatGPT, it will get the same answer. It's very easy to detect the plagiarism, because ChatGPT cannot be customized and give you different answer, maybe. So first of all, so plagiarism concern, I think, is easily answered, I mean, in addition to what Yogesh has said. But yes, it's a definite challenge for detecting plagiarism. And I mean, my thought is that, like, for early school days, or maybe like early classes, it will be easier. But maybe once we go to slightly more complex topics, it will be more difficult. Plus, it takes huge time to train ChatGPT. For example, I was reading that ChatGPT does not know too much about the happenings of last 1 year. So that's why these systems will always remain outdated. And if you restrict your scope of the curriculum, because ChatGPT mostly knows internet, so your curriculum is not what it has covered, then definitely it also cannot give the answer. So these are some of the tips and tricks. I mean, these are not standard answers. These are all, tips and tricks which a teacher only knows how to, find out where students can make mistake and where to catch it.
Yeah, thanks, Sparsh. So, Preeti, you have anything to add, or?
I don't have much to add, but completely agreed with Professor Yogesh's point. So only instructor will tell you which one is. So, and also so Sparsh had an interesting point that, okay, ChatGPT, I have also not used ChatGPT, but ChatGPT will give you the same answers. So, but unfortunately, there is a workaround. There are tools like Quillbot, which will help you just rephrase that same sentence in a different way, unfortunately. So yeah, okay.
Yeah, thanks, Preeti. So there's one question by the audience. I think it should be direct to Raghu only. It's specific for RDU. The question is, how reliable, accurate are RDU chips? Are there comparison with NVIDIA Hopper GPU in this regard? Over to you, Raghu.
Sure. I'm not sure what reliability meant here. I mean, if it's with respect to like mean time to failure, downtimes, stuff like that, I'm not sure if there is any public data on Hopper or any chip for that matter. People tend to hold these close to their chest. But if it's reliability or accuracy in terms of ML training, if you take from like a previously trained checkpoint, you want to fine tune, can you match Hopper or anybody else? I mean, there the answer is, yeah, I think a few slides I had it, we are actually able to exceed the accuracy. So, I mean, the unfortunate thing is, even though the field is big, we tend to throw around the same terms and they mean different things to different people. So I keep saying performance in terms of execution time, but I realize the ML community uses performance as model performance, like how good it is to do a task, which is what I'm using. I'm using the word accuracy for that. So in terms of accuracy, yes, there are certain differences, between FP16 checkpoint versus PF16 checkpoint, and int 8 and things like that. But while there is no exact science on whether FP16 is better than PF16, it seems like the world is somewhat settling on a mixture of FP16 and PF16 right now. Whether there's comparisons to Hopper, well, I mean, the data on Hopper itself is a little sparse to begin with. But in terms of accuracy to publicly known capabilities, yeah, I would say that it has been able to match or exceed what's been published.
Yeah, thanks, Raghu. Maybe the audience has to wait to get those numbers published, and then probably we can come back to this question. Yeah, thanks, Raghu. So another question is very relevant to us. What about partitioning workload intelligently between various heterogeneous systems? Because we have been talking of heterogeneous system. So that's the question. I mean, whoever likes to pick it up, Yogesh, Raghu, Sparsh, I mean, please feel free. So it's not directed to anyone.
Yeah.
In general, they have asked us.
Yeah, I mean, I can say maybe just a short thing, and then I'm curious to hear what other people think. This is, I mean, ML has certainly made its way into these fields, right? I think Google published a paper on this. Jeff Dean and others published a paper where they tried to place the workload intelligently using RL, reinforcement learning. So, I mean, Google being Google, of course, they have a lot of data, a lot of metrics on sort of the overall health of their data center. So I think there's certainly a lot of opportunity. We have dabbled with, like on the research side at least, we've dabbled with similar approaches, at least, and we have seen some success when we try to compile to FPGAs. So very frequently, you kind of want to know, at least one place where I think there was promises. When you're trying to compile to these heterogeneous systems, you often want to take a decision and you want to evaluate the cost of the choice, and you don't have the liberty of just running it all the time. When you run it, that's fine, but you want a cost, and it's sometimes not that bad to build an ML model to accurately predict, like, okay, say I did a partitioning like this, how much is it going to cost? And if it's within some error bound, or if it's going to guide your search in the right direction, that actually turns out it's quite fast. It's quite reasonable. I know there are other people using it in like the chip development life cycles. I couldn't speak to that because I'm curious to learn that myself. But at least as a tool inside the compiler to evaluate cost models, I think it's a very promising thing.
Mm-hmm. Yeah, thanks, Raghu. I think there was a similar question being asked by another person, so I'll just skip that question. They wanted to understand how AI we have been using for systems. So you have really answered this question that there is a scope for using AI for our system problem as well. I'll take another question. I'm just browsing through. So another question people are asking is, we do not see Google being replicated for enterprise. What is the panel's take on ChatGPT for enterprise? I think a lot of attention to ChatGPT, but nevertheless, so I mean, it's open to all the panelists. So whoever likes to pick it up.
Maybe I can go on this first.
Yeah, Yogesh. Yeah.
Google did come out with their Google search appliance for the enterprise, right? Many years back, and it was there for a few years, and they discontinued that, right? So it's not. I think there is going to be it's all a question of where can more money be made. That's the honest answer for the business, right? If you can make more money just with the centralized service for the general purpose workload, right, and maybe have some specialized contract with major enterprises for customization, right? There's no need for specialization, and that's where there might be a market beyond ChatGPT, right? You might have the next tier of vendors who develop large foundational models with the intent of customizing it for enterprises, right? So this is going to be a very interesting market dynamic as well, right? So both from a centralized, like global search perspective as well as specialized ones. But I do see that from the autopilot, right? So from GitHub, right? That's an early example of your ChatGPT being put to use for developers, right? So there is going to be specialization on a per enterprise basis, but the question is how much are you willing to pay, right, for doing that?
Yeah.
And one small point I would like to add, like the previous question was there, whether you can use AI to partition the workload. Actually, my request is please leave some work for humans also. Don't replace humans by using AI. See, sometimes like especially CPU, GPU, FPGA, they are so distinct from each other that a seasoned researcher like us can easily say, okay, this workload will be good for CPU. For this workload, GPU will be good. For this workload, FPGA will be good. Maybe this GPU versus this GPU, okay, you may use AI, but sometimes just depend on humans. They will tell you the right answer. Or to say it another way, like there is a very common saying that in Bangalore, you spend 2 hours in traffic so that, and you reach office so that you can design, how to, you design systems to deliver kirana in just 5 minutes. So if you design, this, like somebody's asking Chat GPT for enterprise, you may spend 2 years to customize, Chat GPT for enterprise, but it will be useful for maybe just three months. And after that, your enterprise requirements will change. So don't think that AI is the solution for everything. You may have 10 enterprises to design your Chat GPT for one enterprise, and by the time market changes. So think from some, apply some common sense. That's a very simple answer to many of these complex questions, that AI will not solve other problems. You have to have some human intelligence also to answer this simple problem.
Thanks, Varsh. I think AI has really overshadowed us. For each and every solution, we, turn to the AI. So thanks for highlighting it. So I'll take another question. I think it is for the TCS research, which I will take in the end. So one question is the audience has written: should we always rely on such heavy, complex models and large amount of data, and address the corresponding requirements? Shouldn't we also try for better quality of data and maybe some semi-supervised method to try and reduce such hardware requirements? So again, address to all the panelists here. Please feel free to pick it up.
Yeah, I have things to say, but maybe I'll wait for someone else to go first, if you want to.
Preeti, I think, want to go next, right?
Yeah, I can take one try. So sometimes so better quality data, so I'll take an example why this is not always possible. You may have heard of these, giant telescopes being installed. Basically, they're this LSST, so large scale sky survey telescopes, and they survey the sky and they collect a lot of data, right? There is, of course, some data filtering done, but at the end, their goal is to look at, maybe what changed from today to tomorrow, or they are trying to find something. So, for example, a very classic example is when we had this the Higgs boson discovery. They had spent, if you have read the articles, they have spent 6 months in trying to analyze that data, because it's hard to understand what you're looking for sometimes. So you cannot always throw away data. So better quality data, sometimes it's not possible to know what data to use and what data to, discard. That is always not possible. So that's one thing I wanted to mention.
Yeah, the possibility is, that's exactly right. There's some cases it might simply not be possible to get good volume of good quality data. So that might just be a luxury in many cases. The two other things that at least the ML community has noticed, I believe there's a paper in ICML or iClear, I forget, one of the conferences where they're trying to compare classic ML to deep ML for structured data, meaning, let's say you already have cleaned up data, you kind of cleanly identified the features. What is the value add from deep learning versus tree-based, like gradient boosting decision trees and so on? It wasn't clear. It was not very clear, because if you kind of know some structure about the data, you probably don't need such a big model to begin with, because a lot of what at least the hypothesis is that a lot of what your model is trying to do is learn some structure in your data. So if you are able to provide that structure somehow for the problems you're solving, that's the thing. And the other thing is this, if I would have to agree with the question as well to the end, which is, yes, there are startups who are solely focused on cleaning up the data. When I say cleaning up the data for text, hypothetically, it's for example, it's the way you tokenize, the way you end up pre-processing the data. That can have a material impact in your training time. this is something that we've observed it, other people have observed it as well. So there is certainly a trade-off there. I would expect that if the models grow to like trillions of parameters, I would expect that would be one of the pre-processing aspect is going to be one of the big focus areas moving forward.
Thanks, Raghu. Thanks for the question. So I think we have only 5 minutes left. Probably I'll take the last question, which is directed towards TCS, and I think I'm supposed to answer it. So the question is, are there any efforts by TCS research in the area of hardware development for spiking neural networks that are quite promising in energy consumption? So the answer is yes. So we have been looking at a couple of models in the space of visualization, where we are looking at analog based spiking neural network, as well as coming out with the right architectures on FPGA based system. And in this direction, we have a collaboration with IIT Delhi, Professor Manan Suri, who is guiding us to look into this space. And we are also looking into neuromorphic computing, which is basically looking at SNN. So a couple of research projects are going on in TCS. Have a look at our TCS research website. And if you have a specific question, please reach out to me. I will connect you to the right set of people who are working in this space. And specifically for other hardware, so this is of the spiking neural network, but we are exploring the state-of-the-art hardware like GraphCore, and even RDU, along with Raghu, and processing in memory, near memory kind of architecture. So we are catching up with the state-of-the-art hardware for machine learning workloads, and we have a couple of POC and assets in this space. So maybe I can stop it there, and please reach out to me or any TCS researcher through the website to know more in details. So I think we are nearing the end of our webinar. Probably I don't want to stretch. We have only 1 minute left. So I will take this opportunity to thank our panelists, Raghu, Yogesh, Preeti, Sparsh, and for wonderful keynote talk and for wonderful discussion. I'm sure our audience would have, make benefit of it and come out with some new research problems. And we will see more of computing system research students around, chasing all of you for working on their PhD problems. So thank you, all of you. And larger thanks to my audience who has been here. Without them, this webinar wouldn't have been possible. So thank you. Thank you, everyone.
Thank you.
Thank you. Thanks a lot.